It's 11 p.m. now. Give me a second. Hello, everybody. Okay, so as decided yesterday, today we will be doing the lead code for graph problem specifically. Uh, Mainly, what I'm going to do is actually also the because I was mainly the problem that I was getting now, I was actually using ChatGPT to give problems. So now what I'm going to do is actually just simply use this frequency thing for this. Let me. Okay. Company is Meta. Topic is, let's just say, depth first search today. Depth first search, graph theory. Mainly I'm just trying to find out the topics related to graph here, so I can just put the filters. I think this is enough for now. Okay, and then sorting by frequency. Okay, so now we have sorted by frequency. So this is the order we'll go today. Let's see how many questions we can do today. Okay, so yesterday we tried to solve this question without actually using graph. So today we will be doing it with graph. Okay, so I haven't come prepared for this. Like every day, this is the only time I sit. So I also like try to learn, like not I won't say learn, maybe re-memorize the whole graph thing again, because again, as I've said, I have forgotten everything. Not everything, maybe I will remember it easily. Okay, I actually have to do one more setup. Okay, see this. I forgot to do the setup actually. This is something I need to prepare better actually, so that at this time I don't waste time of anybody. But yeah, there's too much preparation. Get the iPad ready, connect it. So now we have our this also here. Okay, so let's try to ask ChatGPT to help me remember. Okay, today we will start. We will start DFS PFS problems of Leetcode. I'll give you the problems that I'll do based on meta frequency questions, the high frequency questions from Leetcode. Good. First task, I have forgotten a lot about graph, so So you have to first help me revise this topic so that I can do the problems also. Okay, so one of the things that I would like to ask you people joining here, so if there's anything which you do not understand at any point of time in this, please comment here or please write in the chat. Okay, so let's see what let's see what ChatGPT is going to tell me today. Cool. Cool. The three things to remember. Okay, graph equal to nodes plus edges. Okay, so we have understood a little bit this here. But let us say these are three nodes. Okay, and nodes here. There can be some data structure in terms, let's say like data which it is number value 1, whatever. Like again, you can create these nodes. And edges, what are edges? Edges is the connection between the two nodes. This is what we call nodes and edges. Okay, yes. Okay, now in Leetcode style, graph often hides as a grid, tree, matrix, word transformation prerequisite. So let us say yesterday what we showed you, this type of thing. This is like one representation of graph here, where what we are trying to tell is that like each is this I and j grid is one node, and the connection here simply is based on the whether they are adjacent or not. That's what actually representing the connection here, whether they are adjacent or not. That's it. So there is an edge if they are, let us say, bottom or top. That's one way to say it. So let's say in this case here, if you see there's one here, one here, one here, and these are not connected with anybody else here, so they are independent here. Okay, so now let's see what is talking about traversal. Traversal simply means visiting all reachable nodes. Okay, makes sense. What DFS does here is that DFS is like going deep, and BFS is like go level by level. Maybe I can try to show what exactly this means. So let us say if we are here, so this is like, maybe even though I'm using the word graph, but this is kind of a tree also. But I think the DFS BFS both applies in graph and trees also. So let us say if a graph is also there, tree can be termed as a special type of graph, maybe we can say. Okay, so what exactly DFS means? DFS simply means a depth first search. So let us say if we are visiting this place, let's say visiting this node, now what we're trying to do, from each node we'll first go, whatever direction we go, we'll actually try to go till the depth first. And once we have covered the depth, I think then we come back, and then we cover the, let us say this, we go till here, then we go back, then we come here, then we go back, then we go here, then we go here, then we go, then again we go back, then we go here, and then we go back completely. So depth, this is the depth first search. Whereas the breadth first search is like, let us say we are this node, you first cover this, then you cover this, then you go here, and then you go here, then you use this, and then come here. So let us say what we have done is this, we covered one breadth first, then the second breadth, and then the third breadth, like at a high level. That's what the breadth first search means here. Whereas The depth first search means this is the way of traversal in a depth first search. Okay, go by level. Q, black screen. I'm not getting black screen. What? I'm not sure. What do you mean the black screen here? For me, it shows that it is still showing to people. Pramit, I'm not sure. Like, are you having any issue viewing this? Or if I'm assuming everybody else is able to see. If you're able to see the screen, me speaking clearly, please comment here also. Otherwise, then I have to go and look back to my settings of OBS, which I am using to stream this. That's it. Okay, there's not any black screen from it. Okay, cool. Thank you, Cozy. Okay, visited is everything. Okay, prevents infinite loop and double counting. Okay, what it is trying to tell that whenever you are traversing a graph, we need to make sure that, let us say, if you have gone to a particular node and you have visited it, you actually mark it visited so that you do not come. So, and why this is important, let us say this is connected with this. Okay, now let us say this is the new edge here. So why visited is important, let us say you came here, then you went here, and then you went here also. Okay, now because you are doing it the depth first search, you might want to go here also, let's say, but this is already visited. So if you have not marked it visited, then it will again go back to it. That's why this visited thing won't be important. Let us say if it would be a tree, but obviously there's like these can be circular loop can be formed in a graph. So that's why being like marking visited is very important. In the grids, you mark visited by changing 1 to 0 or boolean visited. Okay, good. Okay. Common meta problems into 4 templates. Okay, now I think this is good thing here. I have forgotten the DFS algorithm also. Okay, so let's see. Do you want me to? Can you help me revise the? Can you help me revise the DFS algorithm also? Okay, the only maintained model here is that if I said go to neighbor, keep going until you can't, then backtrack. Core skeleton works for grass plus grid. Input a start node and a way to get neighbors. Rule 1, mark visited as soon as you enter a node. This prevents cycles and double work. Rule 2, for each neighbor not visited, you again do the DFS. Okay, so let's say what is telling me here, DFS flavors we will use. So DFS for traversal and connected components. Use when, how many islands, is there a path, visit all nodes. So that's kind of a pseudo code here. Let us say if you want to do a depth first search for a particular, let us say, node, this U is the node, you mark that node as visited, and then what you do, you try to find out all the other nodes which are the neighbors of that particular node, and then if they are not visited, you again try to do the BFS here. One thing that we do use DFS for exactly in the graphs is for cycle detection also. Okay, and that is also okay. There is something called directed graphs also and undirected graph also. I don't know. Let me find something. If I have something written, I'm going to cover my screen a little bit here. Let me see if I have written some notes about DFS BFS also. Okay, I don't have good notes of myself. Oh bro, okay, you all people who are here are going to be very lucky today. Let me show why. See this. Okay, you know what is this actually? This is my last year when I was revising everything again. That at that time, I think I kind of created some notes for myself actually. So what I'm going to do is actually go through these notes and maybe revise graph a little bit better before diving into the question. Do you think you all would want me to do this? Because see, main point is that now I also don't remember everything. Like I have like forgotten a lot of things actually, and I was just hiding this because I didn't want to show you my all notes actually. But this is good actually. So I was just checking if I have it. So please comment if instead of solving the lead code problems, I'll go through this and then we will actually try to solve the problem. This is important, I would say, at least for me, like, because yeah, then I will not actually. Okay, please do. Good. Okay. Anybody else? Pramit, Teju. Teju, I know he just joins stream just to do his work. Okay, but yeah, anybody else here? Okay, no worries. Cozy, you are good enough for me here. Only I need only one person to talk to at least. Okay, so this is again what I'm mainly trying to do right now is just I'm going to read my notes here. Okay, so what exactly? Graph definitions, examples, graph ADT, abstract data types. Okay, what is a graph? What graph G is equal to VE is composed of V is the set of vertices and E is the set of edges connecting the vertices in V. Okay, this is like one way of donating it right now. Okay, again V is the set of vertices, E is the set of edges connecting the vertices in V. What is an edge? An edge E is UV. UV is a pair of vertices, so this simply means that UV is connecting. So let us say if we have this graph, let us say A, B, C, D, E. These are all the nodes and we have this connection here also. So first, what is V and E here? What vertices are A, B, C, D, E vertices, and the edges which are present in that graph. What are the edges presented here? AB, AC, AD, BE, and CE, CD, and DE. So these are all the edges representation of it. Okay, so now let's say what is the application. I have mentioned some applications here. Find path of least resistance. This is like a real world application. Networks, roads, flights, communication. So let us say again you have like n number of cities and you have flights which can go from like this direction from between all of the cities, and let us say you want to travel from city A to city B and you want to know, okay, what would be the best route for you. Okay, and that's where the application of graph comes in. Okay, graph terminology, learning graph theory. Okay, adjacent vertices is vertices connected by an edge. Okay, so again, so that again, right now we are going into only terminology mainly here. So what we are saying is that here is that A and B are adjacent vertices. Why are A and B adjacent vertices? Because A and B are connected by an edge. Okay, there is another term called degree of a vertex here. Now degree of vertex means that number of adjacent vertices. Okay, let us say from A we have this and this. Okay, and this. So in a simple sense, degree of this vertex A is 3 because number of adjacent vertices is, again, number of adjacent means that number of connected ones. So degree of this particular A node is 3, degree of B is 2. Okay, now we mentioned E is A and E, A, B is the incident to a vertex A and B. I don't know. Sometimes I don't even know what I've written here. What does it mean by is incident to a vertex? I don't know what I meant at that time when I was writing it. So let's move ahead now. So I have written a question here. What is the sum of degree of all vertices? Okay, sum of degree of, okay, what is the sum of degree of all vertices? So question is that, let us say if you have all these vertices and if you are asked what is the sum of degree of all vertices, what we have already mentioned is each vertex is how many edges, like how many adjacent vertices is have from each vertex. And I'm using the word vertex and vertices exchangeably here, so don't mind here. So now answer is the twice the number of edges. Okay, because we count each edge twice due to the adjacent vertices. Okay, not sure what is the use of this, but I have written it. But again, that's a good thing to know. Okay, if you see, okay, from here you will count this, from here you will count this. So this is again counted twice. From here you will again count this. Okay, the point is that, okay, I'm not sure how to prove this. Maybe the more I will understand, maybe we can then prove it. Okay, bro, this is like so long. This is like complete theory I have written here. Let's see. I'm not sure if this is being very helpful. At least this is not being very helpful for me, but I'll still go through it to know what I have written at least last time. What is a simple path? In a simple path, no vertex is repeated. Okay, what is a path? Path is the sequence of vertices v1, v2, v2 till vk such that the consecutive vertices vi and vi plus 1 are adjacent. Okay, I hope these things are like explainable by default. Actually, I'm not going to explain much in this one. Okay, this is a good thing now. Okay, no, wait, what is a cycle now? Cycle word is that a simple path except that the last vertex is same as the first vertex. Okay, so let us say ACDA is a cycle. A, B and C, there is no path here, so there is no path. BEC is a simple path. Okay, now I understand what I am calling about the path here, a simple path and a cycle. Okay, so why this was important here? So now let us say question is connected graphs here. Now any two vertices are connected to some path. Okay, that's a connected graph. So let us say if in this graph eventually all the vertices are connected, there is no vertex which is not connected. Okay, so this is called a connected graph. And now what is this? If you see here, let us say if this is how a graph is represented here. Now this is the non-connected graph. Okay, any two vertices are connected by some path, like any path. Let us say even though let us say A and this part are not connected directly, but at least there is some path by which it is connected. Okay, there is some path. Even if any path exists, then that is a part of a connected graph here. And non-connected graph, again the vertices, let us say these are not connected actually. Again it's fairly visible actually, like it's not connected, so like it is still one graph. Okay, now we have a terminology called subgraph, subset of vertices and edges forming a graph. Okay, so we have, let us say, this very complex graph I have made. See, now assume that, let us say, if I remove a few of the nodes here, okay, and that's called the subgraph of G. Okay, no worries, makes sense. So now again coming to the connected component here, a maximal connected subgraph. Example, the graph below has 3 connected components. Okay, see, this is the same problem. Let us say eventually when we solve the grid path here, 1 to 1, there are 2 nodes with value 1. This is not a cycle, right? See, each node is unique here. Okay, each node is what? Each node is unique. each node is unique. So it doesn't depend upon the value actually. Maybe the value are same, but if it is one to one, why are you even saying that there is a graph between one to one actually? Like, why would you say that if it is only one node? But let's say if you have two nodes, even though they have same value, but they are still connected. Okay, now here and again, oh, okay, good. So we have mentioned that you have three connected components here. In the island question, the main question is the same thing actually. We are trying to find out the number of connected components, and that's why it comes is that number of, what do you call it? Number of islands. That's word that is being used here. Okay, free. Okay, I was use free here. Connected graph without cycles. Okay, so I mentioned that, okay, graph is also like tree is also, like, I won't say graph is a type of tree, but tree is also a type of graph. So tree is a graph which is connected graph without cycles. So let us say if I have this thing, whole thing, I can say this whole is a graph. Okay, but this is not connected, so I cannot say this whole as a tree here. What they're saying is connected graph without cycles. So let us say this can be a tree, this cannot be a tree, this cannot be a tree, but this is a tree. Okay, this tree differs from the previous tree data structure. Okay, no, here we are using, okay, there's some clarification I have written here. This tree differs from the previous tree data structures because tree data structure has a concept of root. Okay, so there's one more thing here. In the tree, when you talk in terms of tree data structure, actually we also use the word root actually. Okay, uh, so there's no concept of tree here. I think that's where the term free tree comes in here actually. Free tree, we do not have a concept of root. Okay, makes sense. Now connectivity, let n is equal to number of vertices and m is equal to number of edges. Okay, complete graph are in one in which all pairs of vertices are adjacent. Okay, so this is not a complete graph because what it's trying to say, all pair of vertices are adjacent. Mainly, eventually there is a connection there. How many edges does a complete graph have? Bro, it seems that I have just written some answers here, but I'm not sure how I have written these answers. See, you know what this actually is based on? This is actually based on the, I'm not sure if people know this, there's something called NPTEL, National Program for something, which was launched by government, where they actually put a camera in the IT Bombay, IT Delhi classrooms, and the teacher there were teaching, and from there actually that NPTEL videos is what I had studied. Like I used the same videos to study in my college days in 2014, or like maybe 13 also, 12, and even last year also I used the same videos, because this, like, that is, the video is more than enough. Like, I think I might not do the very good job to cover this theoretical basis of this, so I would recommend you all to actually go and watch the NPTEL lecture. Okay. See, let us say by the end of this session, let us say if I also learn everything, I can keep on having these sessions. But yeah, for now this is more than enough. uh, okay, so again, n number of edges, n is the vertices, m is edges. Now for a tree, m is equal to n minus 1. Okay, now see what is saying is that if you have, let us say, n vertices and m edges, you will always have one less edge. Okay, if you have that's only, let us say, if you're saying that, okay, this graph is in tree, then this means that it is connected, so all are connected and there is no cycle. Okay, so there's 3 here and all are connected with no cycle. So you see here 3 nodes, 3 minus 2, 4 minus 3, 5 node, 5 minus 1, 4. Okay, if m is less than n minus 1, then G is not a connected graph. Okay. Bro, this is theory is going to go a little bit more complicated now. Let me see how much it is. Okay. Okay. it seems that I will come to the important point also below. So let's keep on doing this. I hope people have understood at least this part here. Like, if the number of edges is less than n, then it is not a connected graph. That is very clear. Okay, it cannot be a tree. So like tree is like like the most minimum connected graph that can be formed. Okay, smallest number of, okay, what will be the smallest number of edges if it is a connected graph? Then it is n minus 1. That will be the smallest number of edges if it is a connected graph. Hey, are you people getting this, or like it's completely going cozy, bro? You tell me. There are like 3 people watching at least, so please tell me if you all are getting this also, like maybe the way I'm talking, the way I'm speaking. So yeah. Okay, I do not see any comment by anybody till now. Okay, I know there's a delay from my saying. Okay, cool. Spanning tree. Okay, what is a spanning tree? Spanning tree of a graph is a subgraph which is tree and which contains all vertices of G. Okay, so let us say this is a graph. Now, if you see here, let us say if I keep all the vertices, okay, but I have removed a lot of edges here, like this edge is removed, this edge is removed here. If you see, this edge is removed here. See, this edge is also removed here. So what is the spanning tree? Spanning tree of a graph is a subgraph which is a tree, again. When we say tree, we means that we are making it non-cyclic with only making sure all are connected. So we are just trying to remove the cycle here. Okay. So now in this case, because we are saying this is a tree, the number of vertices you can count. You don't want to count, but the number of vertices or number of edges is equal to number of vertices minus 1. Okay. Now failure on any edge disconnects the system least fault tolerant. Oh, see, this is what it means, why this spanning tree is important. Let us say, okay, so let us say you have n number of nodes. Okay, now if it is a spanning tree here, then what you have is you will always have only one way of visiting a particular node. Okay, now when you have only one way of visiting a particular node, then this systems is a least fault tolerant, because let us say if any one edge fails, then that one node is now cannot be visited actually. Okay, so failure on any edge disconnects the system. Good. Okay, now I have written something called the bridge of Koenigsberg. Very complex word here. Let's see what exactly this is talking about. We have this A node B D C, okay, connected like this. Okay, suppose you are a postman, you don't want to retrace your steps while going to each city. Okay, so when saying you don't want to retrace your step, what it is trying to tell that you do not want to backtrack actually, go or travel on the same edge on which if you have already traveled. In 1736, Euler proved that it is not possible. Okay, so let us okay, so somebody proved this, that let us say if you are a postman and you want to visit all the, let us say, nodes, and you don't want to retrace your steps while going to each city, then Euler proved that it is not possible. Okay, let us say if I go from here to here till here, hey, it is possible, na? See, I traveled here. I'm not sure what exactly it was proven here. Let's read further. Graph model with parallel edges. Okay, A is connected to D, A is connected to B, and B is connected to D. Okay, so that, okay, I think what they're trying to say is that there are two edges here from between two modes. I think that's what is called two parallel edges. Eulerian tour, path that traverse every edge exactly once and return to the first vertex. Okay, a graph has a Eulerian tour if and only if all vertices have even degrees. Bro, this is like very complex now. Not very complex again. I'm not putting my going to. I'm not able to put my thought process here. So let's just remove this for now. Now we are going downwards into actually the how to implement graph actually. So let us say what exactly, how do you implement graph, and that's where the word abstract data types comes in. Uh, what you have is size of the graph. Is graph empty? What are the elements of the graph? Positions, swap, replace element. Okay, notation G, graph, vertices V, edge E, object O, number of vertices, number of edges, vertices. There is something called directed edges, enumeration of all directed edges in graph, undirected edges, incident edges. Incident edges, what is this in incident edges? I don't know what is this. Okay, now, okay, this was the, now we're talking about, okay, something I have written for directed graphs here. Okay, let's move ahead now from here. Let's see, this was the lecture 2 on data structure for graph. Okay, this seems to be more interesting to me, at least today. Edge list, adjacency list, and adjacency matrix. Okay, I think these are the three different ways on which how you can represent a graph. So based on different questions, you can decide in which way you want to represent the graph. So simple DS is edge list. Okay, edge list is the most simplest data structure here. Edge list data structure simply stores the vertices and the edges into unsorted sequences. Easy to implement. Okay, finding the edge incident on a given vertex is insufficient since it requires examining the entire edge sequence. Bro, this is like becoming very complex for me. I think, see, when I'm seeing the lecture, maybe at that time I'm writing only a little bit thing, but I'm not getting everything here. But okay, let me still go through it. Give edge, find two endpoints. Give edges, find two endpoints. Okay, efficient. Adjacency list. Adjacency list of vertex is sequence of vertex and adjacent to V. Okay. Okay, so this is what it is, the adjacency list here. It means represents the graph by adjacency list of all of the vertices B, C, D. B, C, D, A, C, A, D. Finding adjacent matrix is simple. Okay. Oh. Okay. And then the adjacency matrix here. Okay, so this is again one representation of graph here, like, so each is okay, you have this 5 nodes here, and here what it telling is that is A and B connected? False. Why have I put, no, sorry, is A and A connected? Sorry, false. And A, B connected? True. A and C connected? True. A and D connected? True. A and E connected? False. Again, so again this is again one way of, because A is connected to three of the nodes here, that's why for B, C, D it is E. I won't say connected, I will actually use the word adjacent. Graph search algorithms. So I have the BFS here. I think that's where it ends. Okay, no worries. This hasn't been very helpful, at least to me. It just, some things are striking now. Systematic search for every edge and vertex of the graph. Graph V is either directed or undirected. I leave this again. Mainly, okay. If graph is either directed or undirected, okay, we'll use adjacency list representation for graph search. Which is they're talking about this actually representation. Breadth first search, I've already told you all. There's a time complexity part also here. I think this is like too much now theory for me now to grasp. I think one thing I need to do is actually watch a lecture. That is very becoming very clear by just going through my notes. Is that if I don't watch my lecture on my own, this will be difficult. So now what I'm going to do is leave this now, and I'm going to actually directly try to solve the question and just learn it actually. Otherwise, my whole time today will get wasted. Okay. Let's see. Let's try to just implement this one problem now. First, let's just leave this for now. Okay, so I'm going to start this problem. Let's start the timer for this problem now. Starting number of islands. Cozy, I don't think this was very useful, this whole session, at least of like trying to go through my notes, but because I do not remember also a lot. So, okay, let's just start the timer for now. Okay, what it is telling me is this. Okay, when you see one, count plus one, run DFS to flip that whole island to 0. TFS stops at water out of bounds. Your task, retype this from memory, don't copy paste if possible, paste your final code here. Okay, I'm not sure what's happening here, but let's start doing this now. Okay, so we are again to this question, same question we tried to attempt yesterday. Given I am across an 2D binary grid which represents a map of ones land and zeros water, return the number of islands, and the island is surrounded by water. Okay, so I think we know the question here now. Simply question is that again here is the number of islands here. So number of islands simply, again in terms of theory, let us say if I talk about, let us say right now what we are, this is like they are trying to simply ask is that the number of connected components. This is the question here actually. Okay, now what we need to do is, let us say every time we start, okay, how do we visit? Okay, let me just write this code, bro. Hey Cozy, you are with me, or you are like you have also lost me here now, because I don't think I am doing a good job explaining right now, but I'm just going to implement this one. Okay, 2 minutes remaining, so 2 minutes have passed. Great. Okay, so what to do here? What to do is start from one point, keep on moving, and okay, are you able to follow whatever I have been saying till now, Cozy? So I'm just going to implement this. So mainly how I'm going to implement this is let's just take a boolean. Okay, let me just take this int n is equal to grid dot length int m is equal to grid 0 dot length. Is there any constraints here? Okay, one thing which is already mentioned here is m and n is at least minimum 1. So let us say there will be no error at least in this line actually. Good. Okay, now see, if you are interested in a lecture na, I hope you have joined my Discord. What I will do, I will try to actually, okay, one thing I can do and you can is that, see, on weekdays, because I have to do office also, so this is like only 2 hour thing I'm doing it. On a weekend, what I can do actually, I can actually take time to first study myself, revise everything, and then come to this and actually teach you better if you want. Okay, but again, only on Saturdays and Sundays I will be doing that part. Okay, so we have int n gram length. So what I'm going to do is creating this boolean variable here, visited, here new int n and m. Okay, now by default everything in the visited would be what? It would be false. Okay, so let's start the loop here. Now what mainly we are trying to do is I will show you I less than n, I plus plus. Okay, and let's say int number of islands is equal to 0. Okay, so now what exactly I'm going to do is, if grid of I and, okay, not exactly this also, sorry, again inside again int j equal to 0, j less than m, j plus plus. Now if grid of I and j is equal to, okay, this is the character actually one, so is equal to this one, then only I am done. And visited of this I and j is equal to false. Okay, at this point of time what I'm going to do is number of islands plus plus. Okay, so okay, so again as soon as I found the first one, let us say first node, I'll say number of islands is at least increased now. Okay, now I'm just using the word DFS right now here. So if I start the DFS from this I and j now, so that first search, okay, let us say if I'm starting the DFS from I and j and I'm visiting right now, we'll not think in terms of the algorithm of DFS here. Think of, let us say if you have this algorithm of DFS here, where if you can just go there from the start from a particular node and start visiting all of the connected components. Okay, and what you do, if you are able to, okay, it will keep this I and DFS I and j will keep on running until it has not covered all the edges. Okay, okay, so now let's, okay, so again, so let us say I do this DFS I and j obviously along with this grid, and I'm assuming I need this also here. Okay, so every time I find a new eye where it is not visited, I do this. Maybe one thing I can do is, instead of initializing this here, maybe I can actually put this here, so that I do not have to pass this visited. Again, why I'm not passing it is because, see, I again, sometimes when you pass a variable in some way, sometimes it actually, in some way, it actually, when you update that particular whatever you have passed, that update is reflected in the previous one, and sometimes it is not reflected in the previous one actually. So okay, hey, is this part good enough? At least for me it is good enough, so I'm just going to go ahead now. So here let us say I'll simply do return number of islands. Okay, now writing the DFS part here now. Public void DFS int I comma int j comma int grid. Okay, now what exactly am I doing here with this? Let me make a few more things here easier for me. I'm not sure if I need this, but I'm still doing this. And okay, so first is, let me say, if I is greater than equal to n, if I is greater than equal to n, and I is j is greater than equal to m, we just simply return because the I and j that we are trying to visit, that does not exist. Maybe say instead of and should be or. If any of I and j is not in our bounds, also, and maybe also this, if I is greater than equal to is greater than 0. Okay, wait, okay, I'm just going to write a few more things here. If I is greater than equal to 0 also, and I is less than equal to n. Okay, less than n. If I is greater than equal to 0 and I is less than n. Okay, no, let's just, sorry, if I is less than 0 and greater than equal to n, so like it's like making sure I is in the bound of 0 and n, similar, or j is so like out of the bounds. Let us say if it is equal to n or less than 0, it is again out of bounds. Similarly, j is, if or j is less than 0 and j is greater than equal to m. Bro, let me do this. This is or. This is also going to be or actually. There has to be a simpler way to do this actually, but let's, for now I am doing this. Again, so again, what I'm making sure is that if I is less than 0, then also this will be true. If I is greater than equal to n, then also this will be true. Or if j is less than 0, this will be true. Or if j is greater than equal to m, again this will be true. So if again any of them is true, we just return, because our I and j are like out of the bound now. Now what we do, if no, okay, we have, okay, the node that we have come from which, okay, the node for which this was called. Okay, okay, second thing, let's say, let me do this. If grid of I and j is equal to 0, then also return. Okay, we have found a like last, like water body, so we return here. Okay. Okay. Mm, okay, one thing that we haven't done here is visited. I have not marked. One thing that I should be doing is visiting this. So let us say if this is not it, if this is not it, then the first thing we will do is here is marking visited true. Let's say let's start with this. So now first thing I'm going to do is mark visited of ij equal to true. Okay. So it is, if it is out of the bound, return. If it is a water body, return. So if it is not out of bound and if it is not a water body, then you have visited a valid node here. Okay. Ideally, I think I should be doing this from here. I should have marked this visited here, but I have not done this. I am doing this here now. We'll see if this is also right or not. Okay, so I think you are able to follow me. Okay, till now what I have done, I have marked this visited of I and j true. Why? Because again, it is not a water body and it is in the bound, and we are visiting this right now. Okay, now once you have visited the node, what next thing you want to do is do the DFS for this with I minus 1 j. Again, so this is like what I'm doing is I'm visiting. Okay, again we have already told that, okay, the island is surrounded by water and connected by adjacent lands horizontally or vertically. Okay, so either above, down, left or right. And how to do this? It is by this. Is j minus 1 and j plus 1. Okay, makes sense. See, for me now, it seems to me that I am done with this. Okay, now let's see it again. What will happen with this? Okay, so we are, let us say we start with this first node 1. Okay, 0 0. Okay, 0 0 was 1 and its visited also was also false. Okay, so we went inside this loop, we did plus plus number of islands and then we started DFS of I of grid. Okay, now again what I am doing, let us say for any ij I am marking it visited. Then I am just exploring DFS from all the directions of it. Okay, so let us say from this one I am going above, it will go out of bound, going left it will go out of bound. I am going down and I am going right. So for, let's say for my right and down, what it will happen, it will create a recursion here now. So let us say from here I visited here and here. Okay, and because this is a recursive loop here, because again see, let us say if a recursion is called with this one. Okay, so what is going to happen is that as soon as it is called, it will again check the grid, it will check it is not equal to 0, it will mark it visited. Okay, now it will again try to, from this place it will again try to visit bottom, left, right and up. For the left, from the left, oh, one thing also I need to make sure is equal to 0 is okay, let me do this. Is this grid is equal to 0, done. Grid is equal to 0. Okay, or so let us say if something is already visited or visited of I and j is already true, if anything is true. Okay, see now, see, this is the case, this is the important thing here, this is why visited was important. Okay, so let's say if I am at this particular edge, like node, and I go in all the direction, left, right and bottom, but let us say if my algorithm is actually telling me, okay, from here one of the, let us say this I minus 1 would actually try to, like this sorry, I minus 1, not I minus 1 but actually this j minus 1 would actually take me in the left side. now. So as soon as it is called, I am, if I would have not done this na, I will be actually going in the circular loop, because I will be always adding it. So now this is important, and this is or okay. So if it is water body or water friend, or we have found a node which we have already visited also, then also we return true. Like return true, like there's no return type here, so it's void only. Like thing just like ending of that path. That path has ended here now. So okay, so at a high level, what I feel is that this is done. Okay, and this is right also. So again, as Leetcode, we have 3 minutes 32 seconds left here. What we are going to do now is just give it to now ChatGPT to actually tell me if this is right. Let's see. Great, you are thinking in the right direction. Visitor briefs. Your code just has a bunch of Java type syntax issue. Okay, so let us say the only issue is the syntax issue here. Visited declaration is broken. You wrote boolean, you visited. Okay. Oh, see, sorry, sorry. Okay. Mm, okay, DFS signature is wrong, and grid should be this int. Okay. Uh, DFS sign. Okay. See, these are the problems which I still do, even. Sorry. Let's see if everything else was correct. Again. Arey yaar, this also has to be like this also, na? See, this is not int. This is like. Okay, you again, you're saying you lie. You never initialized visited. Oh, bro, because I removed it from here, I never initialized it. So I need to initialize it also. New boolean n and m. Okay. And what mistake I did? Your bounds if is missing this closure here. Okay, what I did? Oh, I did this. Actually, I never needed this so many things. Okay, this could have been all been an or. Actually, because if any one is true, we are done. Okay, compare cats correctly. This was also wrong. Good. Okay, recursive call must pass grid. See, I have put in the DFS grid here, but I haven't done this. See the mistakes I have made. When you do not run the code, this is all the mistakes. And what we are trying to do by the end of this, let us say 30-day series, we'll make sure that we are actually able to write code and not make these kind of mistakes. So let us say it did good now. Perfect. Yay! Hey Cozy, you understood? Oh, finally. Hey, there is one more person who is here but not commenting. Are they even here or not here actually? Bro, if you are here, please comment na. But okay, leave it to be. Good. Perfect. This is correct. And again, complexity again. Let us see what is the complexity of this. See, complexity, we have made sure that this is again for loop, for loop, for loop. Okay. So again, in the worst case, let us say if all is 0, it will still go in order n square. And even in this way also, because we are making sure we have these bounds. So again, we'll all like in the end we are visiting all the nodes only one actually. So the complexity is order n cross m. Each cell is visited at most once because of this the way we wrote the algorithm here. Quick meta notes keep in head. Space order n and m for visited. Yes, good. So okay, because we created this visited, so again the space complexity is order n cross m for this visited. and order one extra if you mutate grid to 0 instead. Oh, okay. So this is a good thing. So what it is trying to say is that instead of keeping the visited variable here for boolean, what you could have done, let us say if the interviewer asks you, okay, can you do this question in order one space? Then yes, you can do this in order one space by just marking, instead of actually marking this visited, just make the grid equal to 0. Okay, so now because your visitors have removed this, you don't care about that node at that point of now you never want to visit that node now, so you just mark it 0. Okay. Okay. DFS recursion can overflow on you. Oh, so again, this is also a good thing here. Because this is recursion. See, recursion is good to understand things, but is never good in an implementation if, let us say, in a large scale system. Because DFS is, the recursion is actually, recursion works based on the stack memory kind of thing. Okay, and now when it is based on the stack memory, that stack memory can get easily full also. And so even though we are able to implement this via DFS is not a good solution if, let us say, the range of, let us say, is very high here. Right now here M and N is only like 100 only, 300 only here. Maybe that's why DFS is still good here. I'm not sure exactly at what point this starts becoming bad. Like what exactly is the number of, what is exactly the threshold when you say the word huge grids here. Okay, but the point is that recursion can overflow on huge grids, and that's what it is trying to tell me, that actually BFS is the safe alternative. Instead of doing DFS, we should do BFS. Okay, no worries, we'll go there also. Okay, so now it is actually asking me to do the next questions. Next, any question out of these three here. Okay, so should we move ahead with this one question, Cozy? You tell me. Should we move ahead with this question and do the next question, or should we try this same question for with BFS? That will help us understand both DFS and BFS without going into the complexity of understanding a new question actually. So yeah, tell me bros, if I should implement this question with, okay, if you want me to implement this question again, the same question again with the BFS, I think I should do that. Let me do that actually. Okay, I'm going to do that. Okay, before going to text question, let's implement the same with BFS. Okay, it seems everybody has dropped now. Okay, I'll still keep on going. Oh. I'm a bit tired right now. Hmm. Okay, let's try to do the same question again with BFS. Okay, confirm. We're doing the same question, but this time we'll do it with BFS. Okay. Okay. What understand BFS? BFS version is a great follow-up and interview ready. Okay. So now number of islands with BFS. Okay. The key idea that we have here is when you see one in queue it, mark wasted, then flood fill using queue. Okay. Let's just okay. This seems a bit complicated to me. Okay, we have used queues here, DQ here. DQ is nothing but actually a stack. Actually, that's it. That's what DQ is. Okay. Hmm. Okay, what's string? Okay. You have this NMN, you have the visited array, you have the number of islands here. Okay, it is a direction right, direction row and direction column. Okay. Okay. So for int I equal to 0, you go here, you actually see if it is 1 and visited is false, you actually increase it, you actually okay. I now got it actually. What exactly is BFS now? How exactly you implement BFS? So you actually initialize a queue here now, and what you are doing, trying to do in the queue is actually you put okay, insert it in the queue, mark it visited. Now, what you do while queue is empty, while your queue again we are using the word queue, but it is actually hey, is stack and queues are different thing, na, actually. Okay, see, I have forgotten. See, I know that these are two different words, but I also know that like DQ is actually used for like implementation of stack. So see, I think the point here is simply here. So if it is empty, you actually until you do this until your queue is empty, it has at least one. And what you're trying to do is if take the value, okay, and then do this k equal to 0, k less than 4, okay. You're trying to go through this direction thing, okay, and then you have a new row, you have a new column, and again if it is out of bound, continue. If it is 0 or visited, continue. If not, then again put it in the queue. Okay, so now I actually remembered the whole queue thing also a little bit actually. Okay, in 1 to 2 lines, why do we mark to true when in queuing, not when dequeuing? Okay. As soon as we have okay, this is asking me question, let me think of it. Okay, we are marking it as soon as we have visited, we're marking it visited this true when in queuing and not when dequeuing. Okay, let us say if we keep this inside. Okay, if we do it during dequeuing, then it might come a bit late and we might have added the same node in our queue multiple times. Exactly right. Good. Hmm. Let me implement this also. Actually, I'm tired and there's nobody watching now this stream. Literally nobody is there. I've been streaming this like this alone right now. Bro, this is boring. Okay, I think the only good part of this stream is that just because of this stream, I am actually coming and sitting at least myself at 9 p.m. at least. That's the only benefit here now because eventually nobody is here. Okay. I'm tired, bro. I'm going to end the stream now. I thought I will do it till 11, but there's nobody watching also here now. And I'm literally tired. Okay. I had promised myself to at least be here till. Okay, let's do this, bro. Don't worry. Mm, do one implementation, okay? Don't worry. And then is equal to dot length. And then is equal to get 0 dot length. Mm, Wanted to see how it is initialized. Okay, this is much better. Okay. Q dot add. Visited ing is equal to true. Now while q dot is empty not weighted of is equal to q dot peak I 0 row and column q dot peak 1. Okay, now int. Okay, there's this int direction row equal to -1 1 0 0 int direction column equal to 0 0 -1 1 equal to 0. Okay. See, there is nobody watching the stream, so I'm not caring much exactly, and I'm not saying anything. तेन जिया नाम बड़ा शहर कदा करदा मैं छोड़ूंगा तेरा रास्ता मैं छोड़ूंगा तेरा रास्ता मैं छोड़ूंगा पोल Okay, I think this is good enough. So I'll edit this in queue to mark the visited also. True. Okay. तेरा रास्ता मैं छोड़ूंगा, तेरा रास्ता मैं छोड़ूंगा, तेरा रास्ता मैं छोड़ूंगा, छोड़ूंगा मैं तेरा रास्ता छोड़ूंगा, छोड़ूंगा मैं तेरा रास्ता छोड़ूंगा, तेरा रास्ता छोड़ूंगा. 85% there, but that's the exact issue. Mostly syntax plus two okay, there's two logical bugs here also. Okay, makes sense. Now these. Okay, and use and equal to 0. Hey, where is it asking me to use and? Use and not this, huh? Okay, where is it? Okay, makes sense. Now queue creation is wrong. Okay, it's not array list, it's array dq. See, dq, q tq tq. Okay, use poll to get and remove in one go cleaner and double peak. Oh, okay. Makes sense. And current is equal to this peak, and this is going to be current of 0 and current of 1. Okay, instead of changing that logic, and r is equal to current of 0 and r c is equal to current of 1. No, big logic bug. You set the wrong visited cells inside BFS. You set the wrong visited cells inside the. Oh, so it's not actually the logic bug actually here. Like, okay, it can be termed as a logic bug, but actually my intention was this actually itself. So, okay. Q dot add, instead of saying Q dot add, it should be Q dot offer. Okay, see. Introduced a bug. अरे यार, देखो मूड खराब होता ही होता है, थक जाता आदमी तो ऐसे बग आते हैं, धीमे धीमे आते चले जाते हैं बग फिर. Now it's correct. Good. So we solved same question with both like what, we solved the same question with both BFS and DFS. So I think this is good enough for today's stream, and for myself also, because I am also not tired. Okay, bye.